Hi friends. So today we are going to learn Bernoulli's differential equation. So the Bernoulli's differential equation is also called as differential equation. It is also called as differential equation reducible to first order linear differential equation. So as the name suggests, the Bernoulli's differential equation is reducible to first order linear differential equation. So what is the first order linear differential equation? This point must be known. First order linear differential equation. Just to remind you, let's just go through the first order linear differential equation. In order to understand the solution of Bernoulli's differential equation, we must know the first order linear differential equation. The form of the first order linear differential equation is something like this: dy over dx plus a of x times y equal to b of x. Please remember, a of x and b of x are the functions of x. Both of them are the functions of x. Okay, now, so how to get the solution of first order linear differential equation? The solution is given by a simple rule, that is y equals 1 over u of x integration of u of x times b of x dx plus c. And here u of x is basically the integrating factor. Here u of x is called as integrating factor, and it is given by e raised to a of x d of x. So this is the procedure of finding out solution of first order linear differential equation. Now we would like to talk about Bernoulli's differential equation. So what is the form of Bernoulli's differential equation? So the Bernoulli's differential equation will have, if I want to write, it will have some specific form. So what is the form of Bernoulli's differential equation? So the form would be something like this. It is dy over dx plus some function of x p of x times y equals some function of x q of x and then times y raised to n. Now if you see the linear differential equation of first order, which is having this form, so if you compare with that first order linear differential equation, so almost it is having same form, except there is an additional component has come, which is y raised to n. This additional part is there. So in Bernoulli's differential equation we have an additional part. Remaining things are almost same as the first order linear differential equation. So in order to reduce the Bernoulli's differential equation into the first order linear differential equation, we must have to eliminate this y raised to n. So to eliminate y raised to n, what we do is we divide both sides by y raised to n. First of all, we'll try to remove y raised to n from right hand side. So the step we are going to follow is very interesting. We divide both sides by y raised to n. So let's divide. So divide both sides of differential equation by y raised to n, because we wanted to reduce the given Bernoulli's differential equation to the linear differential equation of first order. So we have to eliminate y raised to n from right hand side. So what you will get is really interesting over here. So the format would change to this. So you will be getting y raised to minus n dy over dx plus p of x as it is. So when I divide y by y raised to n, this, so it will be y raised to 1 minus n, and then the right hand side would be free from y raised to n. We are able to eliminate y raised to n from right hand side. The second part what we can do is, if you look at here, if you look at here, you have only one variable, that is at this particular point we have only one y variable. But here if you look at, we have some y raised to 1 minus n. So this has to be eliminated and converted to a single variable. So to do that, so the next part is I'm going to do is substitute. We don't want y raised to 1 minus n. It has a complicated degree 1 minus n. So I would like to convert this into a single variable having single degrees. I'll do it like this. So substitute y raised to 1 minus n equals to some new variable, let me call v. So when I substitute like this, I can differentiate it. So if you differentiate with respect to x, so if you differentiate with respect to x, you would be getting a very interesting result, that is 1 minus n y raised to 1 minus n minus 1 dy over dx equals dv over dx. Very simple. So that further if you simplify, so that will give you an interesting result, which is 1 minus n as it is, you can see, and here you can cancel minus 1 and plus 1, so you'll get times y raised to minus n basically dy over dx equals dv over dx. This can be further simplified as y raised to minus n dy over dx equals to 1 divided by 1 minus n, and then you will have dv over dx. So now we can easily substitute y raised to minus n dy over dx as 1 divided by 1 minus n. So in this particular equation here, in this equation, so instead of y raised to minus n dy by dx, we can put 1 by 1 minus n dv by dx. Let me name here equation. So let me name this as equation 1 for our reference. I am going to call this as equation 1. Let me call this is the Bernoulli equation as equation number 2. So, and then let me call this as equation number 3. Okay. So in equation number 3, instead of y raised to minus n dy by dx, we can substitute 1 upon n dv by dx. Instead of y raised to 1 minus n, we can substitute v. So the whole equation gets transformed to a new form. Okay. By substituting, we can write equation 3. We can write equation 3 as 1 upon 1 minus n 1 upon 1 minus n dv by dx plus, now again let's see equation number 3 what we have. We have p of x y raised to 1 minus n. Y raised to 1 minus n is v. So it is p of x times v we can write. We can write p of x times v. And the right hand side of equation number 3 is same, q of x. So let me make it as q of x, no change at all. So let me modify, because if you look at a linear differential equation of first order, with dy by dx we don't have any term. So dy by dx is an individual term. Okay, so we should not have any factor of it. So I'll try to make it dv by dx alone. So we will remove 1 minus 1 upon n from here. So simply we'll multiply both sides by 1 minus n. So you'll see that if I multiply 1 minus n on both sides, from here 1 minus n gets cancelled out. Right? This will get cancelled out, and 1 minus n will multiply here somewhere. It will also multiply with qx. So you will get a modified form of differential equation as dv over dx plus 1 minus n p of x times v, that is 1 minus n q of x, right? So let me call this as equation number 4. This is my equation number 4. Now the question is, if you see this equation, it is very similar to your equation number 1, which is first order linear differential equation. Only if you compare with equation 1, you will get ax and bx as some term. So I can write down here, it is a linear differential equation of first order. It is similar to equation 1. So if you compare with equation 1, what you will get? So comparing with equation number 1. So let's compare with equation 1. So you will get what? Instead of a of x, now you have 1 minus n p of x. So a of x becomes 1 minus n p of x. The b of x, if you compare, you will see b of x would be here the right hand side is b of x, and here we have instead of b of x we have 1 minus n q of x. So it is 1 minus n q of x. Alright friends. So now having obtained the value of a of x and b of x, we can find out the integrating factor. So the integrating factor you can write down here, which is we call u of x, which is u of x is e raised to integration of a of x d of x. So it is e raised to integration of 1 minus of n p of x d of x. Just we are substituting the value, corresponding value, and the solution of Bernoulli's equation. So here you can remember the equation what we have just got is in terms of v and x. So the solution will be like in the form of v. So 1 over u of x, that is integrating factor, integration u of x again, and then that is b of x as we know, dx plus c. So we know that v is, we have already done substitution as what? The value of y raised to 1 minus n is v. So instead of v we can write y raised to 1 minus n. So you will get something like y raised to 1 minus n. You will get here u of x is, as you know, e raised to 1 minus n, that's fine. So I will not change it. So integration, again you will have u of x, there is no problem. U of x is the integrating factor, and b of x is nothing but 1 minus n q of x. So it is 1 minus n q of x dx plus c. So friends, this is the what we can say the final solution of Bernoulli's differential equation. This is the final solution of Bernoulli's differential equation. Now let me just give you the complete methodology of Bernoulli's equation, summary of the Bernoulli's equation, how to solve a Bernoulli's equation. So what is the form of Bernoulli's equation? Standard form of the Bernoulli's equation. How it is going to look like? So it will be looking like this: dy over dx, then we'll have some function of x, that is p of x, times y equal to some function of x, q of x, and then interesting part is you'll be having a factor y raised to n. So for this particular condition, if you look at what is the integrating factor, which is normally we say u of x. So integrating factor is given as e raised to, you can look at here, u of x is e raised to 1 minus n p of x. So integration 1 minus n times p of x dx. This is the integrating factor. But the next part is very interesting, the solution. So how to get solution of differential equation? So the solution of differential equation is given by y raised to 1 minus n equals 1 over integrating factor u of x integration of u of x times we have a function, we have 1 minus into 1 minus n times q of x, the function in the right hand side, dx plus c. So by using these simple steps, by knowing the form, then finding out integrating factor, and then you can go for the calculation or evaluation of solution. So by following these three simple steps, you can easily find out the solution of Bernoulli's differential equation. So hope the method is very much understood. You can take some illustrative examples in order to understand the methodology. So we have a very simple example here. We have dy over dx plus 1 by x times y equal to x square plus y square. So we can try to solve this problem by using the method we have discussed. If you look at this particular problem, it is very similar to the standard form of Bernoulli's differential equation, which is dy by dx plus p of x y q of x y raised to n. We have dy over dx 1 over x times y x square times y square. So if you can observe it, you can easily conclude that it is in the form of Bernoulli's differential equation. So comparing with standard form of Bernoulli's differential equation, which is, so if you compare with the standard form of Bernoulli's differential equation, you can easily conclude that the p of x is, value of p of x is 1 by x. Value of q of x is, again you can see the right hand side function, is x square, and the value of index, that is n, equals to 2 because we have y square here. So if you see here, this is going to be, this is the p of x, this one is q of x, and the n, value of n is basically 2. Okay, so now we'll find out the integrating factor. Therefore, integrating factor, so as we know that the integrating factor we write as ux is e raised to integration of, you can look at the method. So integrating factor u of x is e raised to 1 minus n p of x. So let me write down that. First write down standard form, 1 minus n p of x dx, and that would give u of x equals e raised to 1 minus n. 1 minus n means 1 minus 2, that is minus 1. So minus 1 integration of 1 by x dx. So that would be further simplified as u of x equals e raised to minus, now integration of 1 over x is natural log of x. So this can be further written as e raised to natural log of x. This minus outside would go as indices, raised to minus 1, x raised to minus 1. So by the exponential of logarithmic function, we know that the exponential of logarithmic function, their effects gets nullified. So e and ln gets nullified. So the value of u of x you will get is, that is integrating factor you will be getting would be x raised to minus 1 or 1 over x. So we are able to find the value of integrating factor. Now we can go for the final solution. So the solution of, therefore, solution is given as solution, as we know the result, we have already written, solution is given as y raised to 1 minus n 1 over integrating factor times 1 minus n q of x. So I'll follow same method here. Y raised to 1 minus n, I'll write for standard form, 1 over integrating factor u of x, integration of, so that is u of x times integration of u of x 1 minus n q of x dx plus c. So we can substitute the corresponding values. So when you substitute corresponding values, so you would get y raised to 1 minus 2 equals 1 divided by 1 by x, which is integrating factor, integration again 1 divided by x times 1 minus n, that is 2, times q of x is x square dx plus c. So that will be further simplified as y raised to minus 1 equals x. Now I can simplify this as minus 1, and then x and 1x get cancelled out, only x would remain there. So I'll be getting minus 1, the minus comes outside, x dx plus c. We can also simplify it as 1 by y equals x minus x square by 2, integration of x is x square by 2 plus c. So now in solution, basically we are interested about the value of y. So y can be written as, if I bring y that side, so whole thing would come this side, or which is further simplified to, I can get x into x square is x cube by 2, so minus x cube by 2 plus x times c. So if you want the value of y, so y would be 1 divided by x times c minus x cube by 2. So this is something we can call as the solution of, this is the solution of Bernoulli's differential equation. Okay, so this is the way we can easily proceed and find out the solution of Bernoulli's differential equation. So we can do more number of examples to get proper practice. Thank you very much.